Hello, here in this section we're going to look at 2.5, Graphing Special Functions. This section is going to feature a lot of different types of graphs, so I really recommend checking out the textbook videos in the resource section to see more examples of the different types of graphs that we're going to look at. All of these special functions help us deal with special scenarios that we interact with on a daily basis. For example, we often like to use whole numbers and try to avoid negative numbers. Those are things that we do. The most complicated one that we're going to see is involving us doing the concept of at different points in the day we're interested in doing different things. It's going to be called a piecewise function. It's one of the more challenging ones, but it is valid in terms of as the day progresses we often change what we're doing. Some examples of these things are paying people back money. We often round up to the nearest dollar. When you're in a sports game, there's usually a different plan or a different course of action you take for each quarter, and that's going to also be a piecewise type scenario. It'll probably be best to fill in some examples of when we use these types of functions after you've seen them all introduced here to you. The first one we're going to see here is absolute value. So we're going to do a quick recap on absolute value. Remember that absolute value is distance from a center point, and there's going to be two cases because there's the positive case, so moving from the center point in the positive direction, and the negative case, distance from the center point in the negative direction. When graphing, you will want to use a table. We'll also see how to find the absolute value function on our calculator. So here's a quick review. This says the absolute value of x must be less than 4. Now, this one's center point will be at 0. We will later see in future sections how to move the center point away from 0. If there's numbers that are inside here with the x, that would be an example of something to where the center point will move. But for this one, we need our distance from 0 to be less than 4. So what we're looking to do here is I'm going to look at, if here's our center point, distance from that in the positive direction would be this 4, distance in the negative direction would be this 4, and this is an inequality, so we'd be shaded in here. So if I picked any number in the shaded range, its distance from the center point of 0 would be 4. So here's another way that you could see it expressed. All integers whose absolute value is greater than 2. So this one's center point is also at 0. And we need to see a picture of all the integers whose absolute value is greater than 2. Well, if our center point's here at 0, and I'm looking for numbers that are going to be greater than 2, I'd have the 2 and the negative 2. And this time we need our distance to be greater than. So we'd be shading here towards the outside. And we did these back in Algebra 1. This is just a quick review of what absolute values look like on a number line. They made these two scenarios, either where you're shaded in the middle or you're shaded on the outside, often referred to as a made field goal or a missed field goal. Now, an absolute value function, so this is where it's going to be switching over into xy to where it's on a x and y coordinate plane, makes a V-shaped graph. And if you want to see more information on it, check out page 120 in your textbook, and you can check out the different charts and examples on how to graph an absolute value. Going over all of the functions in this one video would be quite a task. So you'll want to check out these page numbers examples and check out the videos posted in the resource tab of your textbook. The next type of function we're going to look at is called a piecewise defined function. This is the one that's going to be most difficult for you. It is a function written using two or more expressions. So what this essentially will be is multiple graphs all taking place on the same coordinate plane, but the graphs start and end with certain endpoints. And so this is kind of going back to that example up above where I said you might have different plans for different quarters in a basketball game or a football game. So we're going to now flip over onto the backside and work on a piecewise defined function. You can also look at page 118 in the textbook to see this, and there will be at least one video in the resource section of your textbook. So here are some examples of piecewise defined functions on the back. Now, what makes them difficult is that sometimes they're going to ask you for the equation, and it's going to have you draw back on some of your old knowledge, such as y equals mx plus b for writing equations in slope-intercept form and point slope. All right, and we'll practice, and via some of the videos and homework, you'll get to see this happening. But here is making a graph of it. So here's a piecewise function. You'll see it because it'll have this little bracket, and then it's going to tell you what two functions, or sometimes even more. Sometimes they'll give you 3 functions. And we're going to graph both of these and kind of see how it all plays in and works. So what I'm going to do here is I'm just going to go ahead and graph this first one in red. I'm not going to worry about its ending point yet. We'll cover that here in a second. But I'm going to graph x plus 2, which would be starting at 2 on the y-axis, and then it has a slope of up 1 over 1 in all directions. All right. So here's a graph of x plus 2. Now I'm going to graph negative x plus 4, which would be a y-intercept of positive 4 and a slope of down 1 to the right 1. All right, so the graph isn't going to stay like this, but this is what they would both look like graphed at the same time. But now what's going to happen is we need to bring in the piecewise component to where it's saying, hey, I only want you to see this red equation when x is greater than or equal to 2, which is this yellow line right here. All right, so when I'm greater than that line, that red function will exist, which means anywhere less than that yellow line, the red function isn't there. So I'm erasing it for all the values where we are less than the x value of 2. All right, now it says less than or equal to, so that will be a filled circle. Right, and it says, hey, I want the blue one to exist when x is less than 2. So what that means is when I'm greater than 2, the blue one will not exist. All right, and since it's less than, it's going to receive here an open circle at the boundary of 2. All right, so here's what piecewise functions look like. It's going to be multiple equations that start and end, and they'll always match up here on these vertical lines of the x values that they give us. The vertical line on this case was x value of 2, so the blue line exists until it got to the yellow line, and then it stops with an open circle, and it picks back up with a closed circle in red, and then travels off. So this is an example of, say for the first part of your day, you needed this type of pattern. But then, at some point in your day, you switch gears, you change classes, who knows? A new type of pattern emerges. That's what piecewise functions look like. You can see an example of one here that's graphed already. We will go through and look at it and write the equations for it. And it'll also ask you here for the domain and range of these. I'm going to use interval notation to help us do this. Now, if we're talking about the domain, remember that's all x values. Now, if we look at this graph, this blue one will travel off to the left forever. This red one will travel off to the right forever, which means at some point every x value will exist. So that's all real numbers. Now, for the range, this, which is all y values, this is not true, because we can see that this is the lowest we ever get. That's a y value of 2. So, and notice it's an open circle, so I will not include it. The lowest we ever get is 2. Now, both of those arrows point up, which means it'll travel up to infinity. So if you think about it, looking at this graph, we will never get any y values lower than 2. But then in terms of what's the highest y value we'll get, infinity, both of those arrows point up. All right, so let's check out this one. It wants us to write the function. So these have arrows on the ends. So let's have f of x is equal to, we'll have our bracket, and we need to name out both of these equations. So we can do it with point slope, slope-intercept, depending on how you want. I typically find if I have a graph given to me, the best way would be to just continue this graph out to see where I hit that y-intercept. Because now I can see that this first equation is going to be, has a slope of up 1 over 1, so a slope of x, and its y-intercept is 2. All right, now the tricky part here is going to be writing in, I'm going to erase the part we added now, is adding in the constraints, which I'm going to do here in a second. Let me finish finding the second equation. The second equation here has a slope of 1 as well, so it'll be x, minus, because its y-intercept is -3. So there's our two equations. Now we need to add in the constraints. So this one was true when x was less than or equal to -2. Because if we trace this vertical line here, you'll see that it travels through the x-coordinate of -2. Now this one, the blue equation, had a closed circle, so it gets the line under the inequality. The red one then picks up when x is greater than -2. Now for the domain and range on this one, both of these are going to end up being all real numbers, because these arrows will point to the right forever and to the left forever. They also point up and down. So all real numbers there. And you can see, if you compare them, that this graph, obviously, we had a low point, right? That's why our range was different. But this one, all different values will be hit and covered. So we'll finish the first part of this video by looking at this piecewise function. And I'm going to go ahead and draw in these highlighted lines here, because I see that there's going to be a change at x is 0, and there's going to be a change when x is 3. So this is a piecewise function in 3 pieces. The first part I'm going to do in blue. It says is -1. So until I get to 0, and it's going to be an open circle because it's less than 0, my y was just -1. But then when I get to 0 here, I'm going to switch to green. I start now graphing y is equal to 2x, which should have a y-intercept at 0, filled circle because of the line under the inequality, and a slope of up 2 to the right 1. Right? And when it gets to 3, also has a line under the inequality, so it'll be a filled circle. And then it says, hey, it picks up at, so I'll do this one in red. When we get to 3 with an open circle, y is equal to 6. So we'd have an open circle, and then our line heading this way. So this scenario, the open circle for the red is on top of the filled circle for the green. So that point would count for the green equation, but not the red. And sometimes they will be stacked right on top of each other, and that's fine. So this is a piecewise function in 3 pieces. And you can see why this is a little difficult, because you're essentially having to do 3 graphs all at once. But it also applies a lot more to life, because there's often different changes we do in the day, such as the changing of a quarter in a sports game, or us changing classes, to where we change our activities or even our moods. Sometimes our moods change as we shift from one class to another or from one day to the next. Piecewise functions allow us to draw those distinctions and see what did it look like before the change, what did it look like after the change. And you could have these in as many pieces as you wanted.